Hello everyone, welcome to my video of my GSoC journey where I'll be explaining about my project Upstreaming Zephyr support for BeagleBone AI64. My name is Dhruv Menon and my mentors for this project are Dhruva Gole, Nishant Menon and Andrew Davis. A small introduction about myself. I'm currently pursuing my bachelor's from Manipal Institute of Technology. My main area of interest lies in firmware development, embedded Linux and hardware design. I'll be recording my journey throughout this period in the blog, which will be linked in the description below. The objective will be in three parts: a basic implementation of Zephyr RTOS on the BeagleBone AI64, an inter-process communication example between a Linux and a Zephyr RTOS, and an implementation of drivers that consist of the mailbox and the TI-SCI client. So at this point, many people may be wondering about the keyword Zephyr. What is Zephyr? Zephyr is a small, scalable, real-time operating system designed for resource-constrained devices, typically used in embedded systems and IoT solutions. It offers a robust, customizable, and secure environment for running applications on a wide variety of hardware platforms. Few of the key features that Zephyr shows is its modularity and scalable approach towards real-time embedded solutions. Zephyr is an open source initiative managed by the Zephyr project under the Linux Foundation. The platform we will be introducing Zephyr to is called BeagleBone AI64. The BeagleBone AI64 is a single board computer developed by the BeagleBone.org Foundation, designed to offer enhanced artificial intelligence capability along with a robust processing power for a variety of applications. Here are some key features of the BeagleBone AI64. The board is powered by a Texas Instruments TDA4VM SoC, which includes a dual-core ARM Cortex-A72 processor running at 2 GHz and a quad-core ARM Cortex-R5F processor for real-time processing tasks. The AI64 comes with a 4 GB LPDDR RAM and a 16 GB eMMC storage, along with an additional micro SD card slot. It comes with a bundle of connectivity options such as Ethernet, USB, DP connectors, and BeagleBone Black compatible GPIO headers. We will be mainly focusing on the SoC of the BeagleBone AI64, the TDA4VM. The Texas Instruments TDA4VM is a tightly integrated system on chip designed primarily for an automotive application, emphasizing advanced processing powers and real-time capabilities. The processor boasts a dual-core ARM Cortex-A72, quad-core ARM Cortex-R5F, DSP cores, and a 3D GPU. It has a separate domain known as MC domain for an additional dual-core ARM Cortex-R5F. The SoC is capable of asymmetric multiprocessing, short for AMP. AMP involves a system where multiple processors operate independently, with each processor assigned specific tasks or a set of tasks. One processor, usually designated as a master, controls the system and assigns tasks for the other processors. In this case, we'll be having Linux running on the dual-core ARM Cortex-A72 and Zephyr running on the ARM Cortex-R4F. Upon closer inspection, the SoC is divided into two domains, the main domain and the MCU domain. The main domain is a dual-core ARM Cortex-A72 with 1 MB of L2 cache memory and quad-core Cortex R5F with 64 KB of individual TCMs or tightly coupled memory, which helps in low latency memory that provides predictable instruction execution. The main SoC in the navigation system consists of DMA and queue management components such as UDMA, ring accelerator, and peripherals. The MCU domain holds two Cortex R5F along with 64 KB of L2 cache. It holds two modes of operation during boot time configuration, which are split mode and lockstep mode. Split mode allows two independently operating cores, while lockstep mode, one of the operating cores, while other one is in lockstep. MCU navigation subsystem is a subset of modules of the main navigation subsystem as instantiated in the MCU domain. The MCU navigating subsystem consists of DMA and queue management components such as UDMA, ring accelerators, and peripherals. Both domains are interconnected to provide connectivity to various peripherals such as SDIOs, UART, USB Side2C, CAN. Remote proc or remote processors is a framework in a Linux kernel designed to manage and control remote processor in embedded systems. where multiple processors or cores are present through which one core might handle real-time operations while other handle general-purpose computing or I/O tasks. The remote prop framework allows the main processor, usually run Linux, to control and communicate with these remote processors. It provides mechanisms for loading firmware onto the remote processors, starting or stopping them, handling communication channels between the remote processor and the main processor. This framework is essential between different processors for efficiency and real-time responsiveness. Traditional Texas Instrument SoCs implement systems control functions such as power management on each of the processing units, such as ARMS and DSP. However, the traditional approach had tremendous challenges to ensure system stability. A few of the challenges included complex interactions between operating systems on the heterogeneous SoCs, lack of centralized knowledge on the system state, and complex implementation and workarounds for the system works. Texas Instruments System Control Interface, or TISCI for short, is a protocol and interface framework developed by the Texas Instrument for communication and control between different processors within the SoC. This is a set of formats and sequence of operations required to communicate and get the system services processed from system control entity in the SoC. Using TISCI, multiple functions are available to us, such as power and clock management, which helps in operations such as controlling the power states of cores and subsystems to transitioning them between active, idle, and standby modes. Resource management, where TISCI defines the mechanism for managing shared resources such as memory regions, interrupts, and peripherals among different cores and subsystems. A secure proxy or sec proxy is used to facilitate secure communications between different subsystems or processors within the SoC, particularly important in systems where secure communication channels are necessary to protect sensitive data and control information from unauthorized access. Secure proxy helps in enforcing access control policies. Only authorized entities can send and receive messages, through which your proxy will help in maintaining the communication integrity and security. The major benefit of the project are Zephyr being a popular RTOS option can help user with BeagleBone AI64 use Zephyr without touching any low-level code and concentrate only on their application. Adding Zephyr support will also increase interoperability with other devices and systems. Simultaneously operating both RTOS and Linux side by side can lead to a wide range of applications that are time constrained. Thank you for watching my introduction video on Upstreaming Zephyr support on the BeagleBone AI64. I would like to thank my mentors Dhruva Gole, Nishant Menon, Andrew Davis for their support, and also would like to thank the BeagleBone Foundation. I would like to also thank Google Summer Code for giving me this opportunity to contribute to the open source community. To know more about the project, click on the link below